Hello everybody. Today, indexes. One of the favorite ones. We're going to talk a little bit about strategies. We're going to not get into quite as much of the optimization stuff as I wanted because of time, but I think that we'll get the gist. This is intended to be primarily beginner level, so hold the questions till the end, please, and we'll just kind of go through everything. So first of all, taking a look, the history, my history, things that I've done in the past, right? 18 years, over 18 years total databases. Majority of that was in Oracle, RAC, clustering, Exadata, DataGuard, failover, standby, et cetera, early online auto auctions for Cox Enterprises in Atlanta, like Java, the first time they did simulcast stuff, which was interesting and fun, especially with all the Java heap memory errors that we had at the time, so that adds fun. But about 2 years ago, I switched over from Oracle to MongoDB. Wanted to go chase the Internet of Things and chase the fun stuff, and probably go a little bit crazy at the same time, because that's what Mongo does to you sometimes, right? So, interestingly, the thing that I like doing is just changing and helping out, working at the infrastructure level and at the storage level, sysadmin level. I almost think that if you've ever considered it as a DBA going into one of the NoSQLs, and you've primarily been an application side or GUI side, you're going to have a more difficult time doing it, or coming from Microsoft. But if you've done the underlying infrastructure, etc., it's easier to do. So one of the big fun things that I did, I worked for BioWare, which is a division of Electronic Arts, and started 6 months before Star Wars: The Old Republic MMO game went live. So that was a crazy fun time. We changed the underlying storage architecture, the underlying schema, and did a lot of stuff there. But today we're not talking about that. We're going to be talking about indexes in Mongo. So just an overview, the typical stuff. We're going to talk about what they are, why you want to use them, what you're going to do with them, and just really what they are. So managing and tuning, we'll talk a little bit about that. Like I said, not quite as much about the optimizer, and then just some strategy and tips and things that kind of I learned along the way. So basically, indexes are pointers. If you want to just boil it down to it, they're references to another location, to things that you're doing. There's a variety of differences, but database index, your definition is right there. Data structure to improve the speed, data retrieval. Basically, you want to find the fastest way to get to your data that you have. And in MongoDB, in all the NoSQL databases, one of the things is you tend to have a lot more data. Now granted, data warehouse have a lot of data too, but it's going to take you hours to get some of the information. We're here about speed, so you want to do it as fast as possible. So you want your indexes to be as lean as possible and as efficient as possible. The indexes and the pointers know where the data are. You don't. The MongoS finds that out from the config server, etc. But anytime, you also have to think about it. Some people, I'll talk about this a little bit later, but some people get index happy. They think, hey, I love indexes. Indexes are my friend. Let's go put them on every field. So we'll talk a little bit more about that, but the thing to remember is, if your application is very write-heavy and you put indexes on them too much, every time you write, you're going to have to also update those indexes, and that has other implications besides just your sheer number of indexes. So then, why do we want to use indexes? Kind of already went over this, but you want to get to your data the fastest. You want to find out the most efficient, fast way to get there, and you want to be able to find documents. One of the things in between a couple of the versions, they had indexes, the index field too long, and they let that slide for a long time in version 2.4. But what really was happening, and Parse customers has this going on, but it's an expected behavior. And what's really happening is when that index leaf is missing, points to a document, that document might as well be gone. You're not going to be able to find it, right? So basically, you want to improve your performance. I already said that. So you have a large collection. There are no indexes on it. You're talking terabytes and terabytes. How long do you think it's going to take you to find that index, to find that document that you're looking for if you end up having to scan the whole entire thing, right? Needle in a haystack. So how long is that going to take you? That's going to take you a long time. With indexes in all databases, not just the NoSQL databases, but also the relational databases, you get certain different kinds, basically 4 basic kinds, right? So you've got your bitmap indexes, which point back to bits, look at the rows, you're going to go through there, and it's good for low cardinality type things, data warehouse type environment, that's always good to there. So basically, it's fast, it's compressed, it's not going to take that much space. Then you've got your B tree, which a large portion of your database technologies are going to use. including MongoDB. The majority of its older school style things are going to be tree indexes. Then you also have the newer style things that are used by some of the new NoSQL technologies, such as fractal trees. Toku uses those, right? It sorts it a different way, branches it out, but you can do multiple things at the same time without impacting what's going on. And then the LSM as well. So you've got basically those. So what do these look like? What do their shapes look like? Two-dimensional bitmap, zeros and ones, bits, just like that. Pretty simple. Your B tree, your main Mongo indexed. The beauty of the B tree is that it isn't self-balancing, right? It keeps the data sorted, keeps it balanced. You know, the majority of the file systems for the databases are going to use that, and each branch pretty much is going to end up looking the same. When you get the fragmentation in there, it still keeps that area in way, it just keeps blank, empty space. So fragmentation is always a big thing in Mongo, especially the older versions, if you're not working with some of the newer compressed engines. Fractals. Now, you have to love that picture. Like, that would be a great tattoo, I personally think. If I were to get a tattoo that would look like that. Or the one off of The Blind Side. You guys watch that show? That's actually, they've got some cool tattoos. But fractal tree, Toku uses that, you know, some of the Rock stuff is looking into it. Rocks is more the LSM. There's a lot of great talks. There are a lot of great talks here for LSM. So I'm not really going to like go over that. That's theirs. But you can just look here. You can see how they do the different merging and how that works. Basically, low-cost indexing by moving and merging pieces and chunks. You know, streaming data works well with the streaming data, highly streaming data. So might be good for some people in this audience. And then you go back to the MongoDB, right? Which is what we're here to talk about, the MongoDB. So you got your default _ID. Basically, it's the one that comes with Mongo. Some people think that they know so much about their application that they should go and change this particular thing to be their shard key, and they're going to change the default value. If you know everything about your application today, yesterday, tomorrow, and in 15, 20 years, then yes, please go ahead and do that. However, if you don't, it's a good idea to go ahead and leave that as is, because it helps you out in several different ways. One, if you don't have a timestamp anywhere in your other collection, you get one by default. Because of the monotonically increasing value of it, you can always use it to find information about when that record happened to be put in place. So that's always helpful, okay? The other things about it, it's unique by default again. If they're using it to further inner systems, you don't want to mess with that. And then two, if you have heavy write systems, or if you're just very, very lazy and you don't want to think about sharding, you can always use _ID hash as your default shard key. And that's for horizontal scaling. Unique, right? It's unique. It's its own special little snowflake. It shouldn't have another snowflake exactly like it. So, and then single field. The majority of the indexes that you use on simpler applications would probably work well to be simple. And that doesn't mean that you have 5 fields. You should have 5 single field indexes, unless your application calls for that. Right? Because wherever you want, wherever you can write a compound index that will get you there faster than all of these single indexes we're trying to attempt to use index intersection. So a compound index done well will always be faster and it'll save more space than 2 single indexes that are using index intersection. Even though index intersection between 2.6 and 3.0x got a lot better. So compound, I already said it. Compound, your order does matter. Okay, in both the query and the result set, the way that it'll be returned. So that's important to kind of distinguish. And then your multi-key index. Your multi-key index, you have to be careful, because you're putting an index on something that has an array. And so you find your element, you go in, when you search through and you find the multi-key element, the first element that it finds is going to match your search criteria. And then it's going to bring all of that back into memory, and then it's going to do the sorts there, and then it's going to portray your results. The problem with that is, depending on the number of elements that you have in the array, that depends on the amount of data that you're going to bring back. Now, I've seen some pretty nasty arrays come back. We had some customers and clients who had 2,000 elements in their search string alone that they were pulling back into memory, and then they were wondering, why on God's green earth is this query so slow? And when you looked, and you saw 2,000 plus elements in their search string for the array, you knew immediately, but that's how they wanted to do it. It took a long time to convince them that they needed to find a better way to do that. And one of the better ways to do that is most likely outside of Mongo, using some kind of queue system or like Redis or something else, maybe an Elastic. So multi-seed. The other thing you have to worry about, when you are indexing the array, it's going to put all of them and treat them differently in terms of storage and space consumed. So you not only have to worry about the memory when you pull it back and when you query it, you have to worry about the size consumption on disk, and then if it's not a compressed engine, you also have to think about the fragmentation that every update to that array makes. So those are some considerations. I'm kind of going to go over those as I go along, as opposed to one big dump of strategies and tips at the end. So then we'll continue on. So I talked a little bit about the multi-key already, but there are other considerations when we're talking about multi-key, and those are here, right? Pretty much straightforward. One and only one in an array can have the multi-key on it. You know, if one already exists, it's going to fail. Your insert will fail to that element. So it can't be a shard key. They're going to impact performance, like I said before, not only when you're putting the data in, but when you're updating the data, when you're pulling the data out. Okay? And hash, no on the hashes. And it doesn't work for covered queries. Whenever possible, you want covered queries, right? It makes total sense. If your query is covered, you're going to have happy queries. You're going to have a happy application. You're going to have happy customers on your end and on our end, because it's going to come back sooner. So that's what I was talking about a minute ago. The whole array, the first element only, and the memory usage. Those are things and considerations that you should watch out for. Other things, there are other limiting factors both in Mongo and related to indexes. So, no more than 64 on a collection. You might think, oh, I would never in a million God's green years put 64 indexes on a collection. When I first started working with Mongo, I don't know how many clients that I would go into and look at their system, and they had all of these indexes, and a lot of them, they didn't even know that they were almost exactly the same index. And the problem with that, they were using like RoboMongo or some of these others. And even recently, the most recent version of the updated RoboMongo, it's not displaying the index fully and correctly. I had a customer the other day that was called in, and it's like, hey, is this TTL working? You know, I don't see it being defined in my RoboMongo. Well, you go in and you look in the system, it's like, yeah, your TTL's there, because he was like, it seems like the data's getting removed correctly, but I don't see the TTL there, so how is the data getting it removed? Is the application doing it? What's going on? But went in and looked, and yes, the TTL was there, but it was just not being displayed correctly. And so that was actually what happened to one gentleman. He was using RoboMongo, and he had no idea that he had all of these indexes, and he was very, very close to that 64 limit. Why not have all those indexes again? Space, performance, write. If your application is heavy write, heavy update, and you have excess indexes, it's going to have to update those every single time, and it's going to end up negatively impacting, okay? So you have to think about all these other considerations and all these other factors when you're thinking about the indexes that you're putting in place, and when you're thinking about the queries that you're writing. You always have to think about your workload, always. You need to know what your workload is. I mean, us at Object Rocket, we may not always know what your workload is, but if we've worked with you for a little while, we should get to know what your patterns are. And if we haven't worked with you for a while, hopefully the refresh rate will come back pretty quickly on the old brain cells. 1024 bytes. Most of these are like total no-brainers, all right? But again, what happens if you pass over that particular mark? You'll have the space problems, and then you'll have inserts that are failing. And then with the MAP versions and the older versions, you'll have fragmentation, less so with WiredTiger. WiredTiger keeps it compressed in memory, so it doesn't have to do the uncompression and then the recompression. But it does impact things such as your overall cache used when you're querying, and that can have an impact because of the way that they've set aggressive eviction threads for pages out. So anytime you run into that, you're gonna have a problem. Namespace files, those are just some givens, right? Max fields, your index names. Now this brings up an interesting point. Everybody said, MongoDB Inc., their guide actually says, you don't have to make your field name super small. It doesn't really save you anything. Space isn't really a concern. But my friend and colleague ex-colleague David Murphy has an excellent blog article out there on this, and he very clearly will go through and give great examples on why it matters. And it's not just about the size, it's about the network traffic that you're incurring, and it's also about the memory. You're bringing all this in when you don't have to for no reason. That's another reason you should look to utilize projection when possible on your queries, because if you don't have to bring back the whole entire document, if you don't care about the whole entire document, don't bring it back into memory. And this really comes into play with the WireTiger stuff, because the cache is so important, especially depending on how you allocate the cache, the amount of cache that it's going to use. Because WireTiger is kind of like Oracle back in the old days, or the medium days, when Oracle got better with memory management and started using more of the shared pools and all these Java pools, and etc. Because it prevented Oracle from slurping up all the memory, right? MMap will use all the memory that the system has. WireTiger is supposed to not do that, but when it starts thrashing the cache and utilizing everything that it has and gets to that eviction threshold, 80 to 95%, then it will start using the system memory as well, and you will start seeing OOMs. I think some people in this room may have seen that. So, the size of a network, then you have to also think about your replication laws that are in play, and any journals. Just, you're going to use up more space in everything that you have. So it's not just the one size fits all. So now we've got specialty indexes. So this is like one of those situations where I like the fact that today's database world has changed. It's no longer, hey, use Oracle. Hey, use MySQL. Hey, use SQL Server. Hey, use Mongo. It's like, use the tool for what it does best. Polyglot persistence, polyglot programming, right? Use the tool for what it's worth. Personally, I've seen quite a few implementations and utilizations of geospatial in Mongo and attempts at text. The tools that exist out there are far better. For example, Elasticsearch and its improvements with geospatial in the latest release, I would highly, highly, highly suggest that you utilize either Elasticsearch or something else for the text and for the geospatial. So, and then if you wanted to talk about Mongo and geospatial, that would be hours and hours worth of work, and just do it. So despite the improvements that Mongo has made, and they've definitely made improvements, I would say use the correct tool. So, and I kind of just point that out there. There's your index, your savings, in terms of just text searching, 50% faster. I mean, really, really good stuff that they're doing there. And the beautiful thing about that, ObjectRocket now has a connector directly from Mongo to Elastic. So, next time, we're going to go ahead now, Sparse Indexes. So, Sparse Indexes, it's really only for the fields. It's intended to decrease the size of your index and thus make it faster. And it does that by only indexing documents who have the field that you want in them. So, if a field middle name is missing, it wouldn't index that particular field. So that's kind of how that's supposed to work, and kind of how it does work. However, the partial indexes that we have now in 3.2, they're supersets of the functions. They tend to work significantly better. So I would say use those. Shard key indexes, sharding is a whole entire different topic, right? But just a little bit of the basics there, and then there's a little bit more about them right here. And really, this is just the nodes, because you have to spend a lot of time, when you're thinking about what your shard key is going to be, you have to do analysis, you have to do query patterns, you have to do profiling, and you should really, really, really take time, because shard key, if you're in a sharded environment, is the single most important thing that you can do, is spend the time to figure out your correct shard key. Because large collections, if you pick the wrong shard key, and then you have to dump and restore something that's really anything over 30 gig, it's going to take a while. It's going to take a long while. Other limitations with shard key, right, makes sense. Obviously, your shard key, you wouldn't want multi-key. You wouldn't want it to be text, and you wouldn't want it to be geospatial, because two things can actually be at the same spot. My foot, my shirt, my whatever else are all exactly pretty much at the same spot. On the 2D sphere, at least, right? So I just wanted to kind of briefly go over, just put them out here for you, how you would create the indexes required for sharding and how you would do the sharding. It's pretty simple for that part. All the stuff comes in either before or after the beginning. And then time to live indexes. Basically, this is a great way to automatically delete. things. Now, there are a couple of caveats to that. What you have to be careful about is if you have a social media app and you know that you're busy Thursday, Friday, Saturday, Sunday, and you set a 7-day delete, that means that every Friday, Saturday, Sunday, you're going to hammer yourself deleting last week's stuff. So what you need to do is do like a 3 or 3.5 day offset for your time to delete. Because you usually do it expire after seconds. So, and you would get hammered at the top of every minute because that's when the thread kicks off, the TTL thread monitor. So sometimes you may be watching your Mongo stat, which you should always be doing whenever you're doing massive deletes anyway, and you're like, why does this happen at the top of every second, at the top of every minute? And then as long as it stays there and it goes away, stays there and goes away, you're fine. But if it's there after like 10 seconds, then you probably need to take a look at that. So here's some basic syntax for create systems. Later I'll have a very difficult to read TTL slide, which you'll be able to read it on the slide deck, right? But you're probably not going to be able to see it here. But here's some basic index create statements. Super simple. Used to be ensure index, right? Then they changed it to create index, which makes sense because that's what all the other database technologies do, right? But I'm sure someday they may actually deprecate ensure index, and then drop index. Whenever you create indexes, just the caveat, 2.4 and even into 2.6, if you put, in 2.4, if you create an index and you put background, it created in the background of your primary, but it created it as a foreground process on your secondaries, and so it would hammer and freeze your system because by default, creating the index is a blocking operation. In 2.6, they fixed this. I didn't trust it fully till like later versions of 2.6, and I would still, for larger indexes, for larger collections, for anything like multiple gig, I would still personally be careful. My friend over here, Jason, has done some larger ones, and has trusted the system. That I'm a little more old school that way. But sometimes you have to do things because you need to get it done faster for whatever reason. So there are things you can do. How to get indexes, all this is basic. All this is stuff that is in there, right? So tuning indexes. A lot of times the order of the fields don't matter. In the single field indexes, order doesn't matter. It can go up the tree forwards or up the tree back, and it doesn't matter. But again, on the compound indexes, it is going to matter. So figure out what you're going to do, what it is that you want to do, if you're going to be doing range values, if you're going to be going straight there. You need to watch out for scan and orders in your explain plans, because that means it had to do the whole entire thing, right? So, which more docs in memory is going to eat up your memory. You're not going to be able to do other things, CPU times. So, and covering. So I kind of mentioned this a little bit earlier. If you have covered queries, you're happy, right? It's going to bring back exactly what it finds, exactly what you ask in a particular way. So this is just a little snippet there, and then I think you have this one, projection. Yeah, the covered word's coming in just a second. So projection, this is a lot of words about projection, but basically just saying that if you know what you're looking for, and you know exactly what you want, and you don't need all the extraneous BS, don't bring back the extraneous BS. And the beauty of that is, that was loud. The beauty of that is that a lot of times it won't even have to go to disk to get the information that you're searching. So obviously if it doesn't have to go to disk, you don't have the page faults, you're going to be a lot faster. So, boom, there it is. And here's an example of the covering. And it also kind of incorporates the sort order thing that I was talking about. It talks about the scan and order, right? So on the left, you've got your query, you've got your suboptimal index. I love that word too. Suboptimal index, right? Country, and it's going to go down through there, and it's going to look, and it's going to pull this in there, and then it's going to have to do your sorts in there, right? So that's where it does the full in-memory scan and order. Whereas if you change it and you limit what you're bringing back from the beginning, based on putting the correct index, based on what it is that you're going to. This is where knowing your query patterns and what they're going to be matters, right? When you're creating the indexes and you know what your query patterns are, it really, really helps. So, but anyway, you go over there, it does your order, it already has it sorted, and you don't have to do the super expensive CPU intensive scan and order. And here is where the slide was out of order from earlier. Here's the TTL reducer. You actually can read it, which on my laptop you couldn't, so I'm surprised. But this is a snippet, and what this does, when you run this, it has variables built into it so that at any particular time, if you're hurting your system too much, you can stop it. It has an out, right? So that's the beauty of it. Pretty simple. You put in exactly you figure out your time. There's some other associated queries that I don't have up here, but you figure out, how many documents that you have that you're going to want to delete, because obviously the more that you have to delete, the slower that you're going to want to do that, and also depending on when you're going to be doing the deletes will matter, because you don't want to do the deletes in the biggest part of your busy time, right? Especially if you're already a write-heavy application, or if you're doing like batch deletes or batch inserts or any other write application. But this is actually, it's been very, very useful, helpful for us in having to clean out some of these. We've had to help a lot of customers do things like this. So what happens if you have bad queries? You fix them, right? You want to tune them, you want to change the query, you want to do whatever it is that you have to do. So here's a log entry for some of these bad queries that we have. This is what you would look for. These are things you would see. Obviously, if you see the call scan in there, that tells you that you've just had to go through everything to find what you're looking for. You see how long it took, 3081 milliseconds, right? But you also look at the in scan and in return. You returned one result, and you scanned 83,000 documents to return one result. Obviously, that's not optimal. So what do you want to do? You're going to add an index, because you want to do whatever you can to avoid the entire scan. Earlier when I was talking about the super large table, it was like 2.3 terabytes, the single table. Imagine doing a call scan on that. Now granted, the average object size for that particular collection that I'm talking about is only 252, but still, it has 10.5 billion documents in there. Even with only 2 fields and 252 average object size, it's still going to take a while to get your answer back. How you do your answer, this is what you do, avoid that. Here's another query. Take a look at what's in there. Again, you're looking at your milliseconds that it took to complete. The one, your in scan, 44,000. You don't want to scan more documents than you have to. So you want to, when you're looking at the indexes and you're looking at the fields, go back to your query, see what it is that you're really wanting, and look for the things that have the cardinality and the distinctness that would allow you to limit what you're bringing back from the very beginning. So, okay. Another one here, right? Another example, only 125 milliseconds on that one, only 113, but there's still things that you can do to fix it and make it more efficient. So the things I was talking about before, I had the explain plans, but I was worried about running out of time, and so did not put those optimizations, because I was going to go through the optimizer with that. So what does that say about indexing overall? We've talked about the fact that you should not have too many indexes. We talked about how you should define some of your indexes and what fields you should use, and use projection and this kind of thing. So I always like to think of indexing kind of like Goldilocks and the Three Bears, right? Where you go in and you say, oh, this bed is too big, this bed is too small, this bed is just right, this porridge is too hot, this porridge is too cold, this porridge is just right. You want to be just like Goldilocks, eating all the blankety-blank bears porridge and having the best bed, right? That's what you want to do. So, and then here's some other things that you want to, so here's some bugs, some cockroaches that we kind of run into lately that are associated in and around indexing. So, data loss during chunk migrations. That's a fun one. I've got a little bit more about these, right? And then you talked about WiredTiger. I talked about the cache that they have and the eviction cache. There are also some thread settings, and it gets a little bit aggressive, and it would use up all your memory, and it'll do things that you don't want. It also has a preference right now for removing index pages first. So, doing another thing that's not out there in the JIRA system, but we ran into it and found it on a message board from like 2013. It involves the cursor. And like when you're doing long-running operations such as backups or initial syncs, and you drop an index, it kills the cursor. And you can, then if you have to recover, if you're planning to actually recover from that backup, it's going to be incomplete backup. Or if you're planning to well, if you've initial synced something for a particular reason and the cursor died, that's not a complete sync. So here's a little bit more information about those, including the list of the bugs, but I pretty much went over that. The biggest thing, there's a workaround for the first one. Turn off the balancer or upgrade to 3.11. And then the aggressive evictions, that one currently is not supposed to be fixed until 3.3. So there are a couple of other associated bugs around that bug that were fixed in 3.25, but not that one. So I thought that was kind of interesting. And then the older version of 2.1, if you step down, you're going to lose data. So that was just kind of well, I hope that doesn't happen to you kind of thing. But you have to watch the cursor. So, and then I'm done. Yeah, that's interesting. I should have left those optimizer pages in there after all. So, all right. If you guys have any questions, you can come up and grab me. So.